All right, 21 out of 40 was the average for this. Question 1, the most atoms of oxygen. Well, if I work out the moles and then convert it to number of particles and then to atoms, that should do it. So moles is mass over molar mass, so 64 over 32. That gives me the moles of O2. Multiply that by 6 times 10 to the 23, and that gives me the number of actual O2 molecules. And then I have to double that number because I want atoms. And there's 2 atoms for every 1 molecule. I'm not going to work out the numbers, I'm just going to compare them. For the next one, I've got 1.2 times 10 to the 24 molecules, so I'm going to need to double that to account for the fact I want atoms. Are those the same numbers? Yes, so the first 2 are the same, so that's wrong. Next up, so how many moles do I have? Moles is mass over molar mass. The molar mass is 3 times 12 is 36, plus 6 is 42, plus 90. 90. Multiply that by 6 times 10 to the 23. And I've got to multiply that by 3 because for every one of those molecules, I've got 3 oxygen atoms. All right. And for the last one, I've got 1.2 times 10 to the 24 multiplied by 3 because it's 3 there. So what's bigger, C or D? 3. Yeah, D. Okay, next one. Empirical formula. That should be nice. So write out the atoms or the elements in big. Put the molar masses down. And then put the mass or the percentage above each one. 24, 3, 1.6. All right, let's do the maths. C2H3O, 0.1. That smells wrong. Let's carry on. Divide everything by the smallest. And that gives me C20, H30, O1. Okay. Yeah, that's right. That's A. So 2 is A. That's weird. Question 3. That relies on the fact that 1 mole of any gas at STP is 22.7 decimeters cubed. So if I know the moles of oxygen, let's say it was 1 mole of oxygen, then I know that it would be 22.7 decimeters cubed volume that I need. All right then, so moles, mass and molar mass. Moles, mass, molar mass. So the mass is 5.8 and I know the molar mass is 58. So that gives me 5.8 over 58 for the number of moles of butane. Now for oxygen it has to be 13 times bigger than that, so 5.8 over 58. Oh, I haven't balanced it right. There's a 2. That 2's missing there. Okay. So it's not 13 times bigger than that. It's going to be 13 over 2 times bigger than that. Okay. So that's the moles of oxygen. And now I want to know the volume. So then I'm going to have to multiply that by 22.7. So in this box, that's the actual volume of oxygen. What's that then? B or D? The answer is B. So 3 is B. Nasty. Question 4. The relative molecular mass of bromine. Oh, I remember doing this one when it came out. Oh, it's pretty nasty. I think there's a trick in it. I think the trick is it wants to know the relative molecular mass. So that's Br2, not Br. So for Br2, it has to be the bigger number. It's going to be about 160 is my answer. So I think you can exclude C and D. You can exclude C and D because they're using the 79 and 81 values. Not for the molecule, that's for the atoms. So it has to be A or B. I'm not entirely sure why, but the answer is B. I can do these isotope questions, but I don't recognize this kind of style. The reason the answer is B is because that's a number that comes out closest to 160. That's not the right way to do it, but that's the answer, the one that comes out closest to 160. If you do it by A, it's well off of that average of about 160. Question 5 is the second easiest, which represents a p orbital. So S is a sphere, P is a propeller, D, some of them look like donuts, and F, no one knows what they look like. Anyway, so it's going to be C, isn't it? C, so the answer is C. A is actually a hybrid orbital, and D, I'm not even sure what that is. Okay, so question 6, consecutive ionization energies. Consecutive elements. Okay. So first ionization energy, that's a measure of how easy it is, to pull an electron off of the valence shell of a gaseous atom. So it's really easy to pull the electron off of francium because the electron's furthest from the pull of the nucleus and lots of shielding. And it's really hard, very high first ionization energy, to pull the electron off of a helium, very teeny weeny, no shielding, electron close to the pull of the nucleus. So why is X has a greater first ionization energy than Y? Let's look at the answers. So as I'm going across the period, all of a sudden it gets easier than I expect to pull the electron off. Easier, needs less energy. So why would it all of a sudden be easier to pull it off? The element Y loses an electron from a different sublevel. Could be. Element Y has a smaller atomic radius. So Y does have a smaller atomic radius. As you cross the period, they get smaller, but that would make it harder. That would make it higher energy to pull it off, so it can't be B. C, element X has a full octet. I think that's a distractor. That's an A-level kind of idea. Taking electrons off of full octets is it's not an IB level idea. And D, element Y has a greater nuclear charge. It must have a greater nuclear charge, but if Y has a greater nuclear charge, that means it's going to pull all the electrons, attract all the electrons in closer and give it a higher first ionization energy. So by a process of elimination, it must be A. Is it 6A? It must be A from a different sublevel. Question 7, the easiest question. So let's go up to the periodic table. Argon's here, so it has 18 electrons. So Br minus would have 36 electrons because it's 35 plus 1. It's not that. Ca2 plus, yeah, that's the answer, isn't it? Ca2 plus, because it has lost 2 electrons and now it's only got 18. So 7 is B. 7 is B. Question 8, the correct in going down group 1. So group 1 is here. Melting point increases? No, as you go down, the melting point decreases. It looks like probably francium's going to be a liquid. They've not ever collected enough to check. Francium's probably going to be a liquid. So the melting point decreases. Metallic bonds get weaker as you go down, as the ions have a smaller charge density. That's the word I'm looking for, smaller charge density. Reactivity decreases. No. Francium's probably the most reactive metal. First ionization energy increases. No, it decreases. As you go down here, the atoms get bigger and bigger and the electrons are further from the pull of the nucleus and there's more shielding. So no, it gets easier to pull off the valence electron. So electronegativity decreases. Yeah, that's it. Electronegativity decreases. The answer must be D. The highest electronegativity is fluorine, and whatever direction you go away from fluorine, the electronegativity will decrease. So that's going to be 8D. 8D. 9. What's the overall charge of the chromium complex? Oh. I put Z, it should be X. All right, so water's neutral, so I can ignore the water. Chlorine, well, it's chloride. If it's going to be a ligand, it's chloride, so that's -1, -1. And so what's the charge of X going to be? Well, what do I know about chromium? I know chromium must be +3. How do I know that? Because it says chromium 3. So 3 -1 -1, it's all got to equal X, hasn't it? And so that gives me a +1 oxidation state. Now, is the IB going to try and trick us? Because it wants to know the charge. The charge is 1+, but the oxidation state mathematics gives us +1. So fussy. Don't know why they bother about that. So yeah, B. 9 is B, isn't it? Yeah, 9B. 10. What compound contains ionic and covalent bonds? So that's going to be, it's going to be the last one, isn't it? Doesn't it contain sodium ions and the hydroxide ion? So I see 2 charges there, and this is covalent. The other ones, Mg2+, O2-, no, that's just ionic, isn't it? For this one here, it should be a 2. For dichloromethane, no, that's covalent bonding, isn't it? It's an irregular tetrahedron, blah, blah, blah. And this one here also, it's all covalent bonding, isn't it? You can draw out those nice Lewis structures. So the answer is going to be 10D. Yep, 10D. 11. Most likely to be ionic. So I think ionic, salt. If they ask me about covalent, then I think maybe about something like water or sugar. But if it's ionic, I think salt. Okay, so melting point. The melting point of salt is going to be high. I've never managed to melt salt. Strong ionic bonds. The solubility in benzene. Well, benzene is non-polar. And remember, like dissolves like. Ionic has a charge separation, a plus and a minus. So that's going to want to dissolve in solvents with a charge separation, such as water or maybe ethanol. So it shouldn't dissolve. So nope, it won't dissolve in benzene. Benzene is non-polar, and salt only dissolves in polar substances, such as water. And electrical conductivity is a solid. So let's think, freely moving charged particles. In a solid lump of salt, are there freely moving charged particles? There are not. They aren't freely moving. So it won't. It will be an insulator. So what have we got? We've got high, low, low, high, no, no. So that's D. 11D. 12 delocalized electrons. So I've got this molecule here. Or I think they're referring to phenol. That does have delocalized electrons. That's what this circle going on here is. There's a single bond between the carbons next to a double bond. This one over here is the ethanoate ion. The ethanoate ion, and so that's got that and that. Yeah, there's a double single bond and it resonates here. There's this double bond, a single bond. Go out like that. And the carbonate ion, well, that actually has 3 resonance structures, as that double bond bounces around in those 3 different positions. So I think the answer is all of them. 12 is D. 12 is D, yep. 13, all carbon atoms are sp2 hybridized. So if I've got a carbon with only sigma bonds, it's sp3. If I've got a carbon with 3 sigma and it's got a 1 pi bond, then it's going to be sp2. And if I've got a carbon with 2 sigma and 2 pi bonds, it's going to be sp. So they want to be just a pi bond. Alrighty, so let's look at A. C2H2. No, that is sp and sp because there's each one has 2 pi bonds. So it's an A. What about B? C2H4. C2H4. Well, that looks good. C2H4. Each carbon has 1 pi and 3 sigmas. Let's keep on going with B. H2CO. So that's methanol. H2CO. Yeah, that's looking good. Pi, sigma, sigma, sigma. And Hoku. So that's methanoic acid. Methanoic acid. So there's a pi, sigma, sigma, sigma. So it's B, isn't it? 13B? Yeah, 13B. Question 14. Specific heat capacity. What's the enthalpy change in joules? I always thought enthalpy was in joules per mole. I think that's a mistake. That's what we're looking at, isn't it? MC delta T for the enthalpy change. So what's the mass of what's being heated? 5 grams of water. What's the specific heat capacity of what's being heated? And here's our little trick, 4.18, and that's going to be kilojoules per kilogram per Kelvin. So there's a unit trick there, grams to kilograms. So I have to fix that. Now they want it in joules. So one way that you could fix it is if I want this with joules, I can knock out that K and I can knock out that K, and that works. I multiply that by the temperature change, which is from 10 to 18, so that's going to be 8 degrees C, which is the same as 8 Kelvin. The difference of 8 degrees C is the same as the difference of 8 Kelvin. Well, it isn't C or D because they're messing me around with the Kelvin there. So A or B? Isn't it B? No, bollocks, it's A. And so, yeah, the answer is A. 5 times that times that. It's just A. Nice. Question 15. Now, rather counterintuitively, the answer for this is reactants minus products, which might smell a bit fishy to you because normally it's products minus reactants. But let me try and prove it. Okay, I'm going to do Hess's law. So the delta H combustion for carbon, burn 1 mole of carbon, and the delta H combustion for carbon monoxide, burn 1 mole of that. And that gives me those 2 equations there. Now I have to combine them to make it look like the top equation. So what am I going to do? If I double that one, and then flip it around, it will add up to that top equation. So remember, if you double it, you've got to double the delta H value. So that happens for both equations. And if you flip it around, the reactants and products swap places, you have to change the sign. Just add that up. That comes out at D. 16. Wow. That's horrible. Well, let's start with A. So let's have a look here. As temperature goes up, delta G, theta, goes down. All right then. So equilibrium shifts. So if I increase the temperature here, if that goes up, then this goes down and becomes more negative. This delta G becomes negative and more negative. Okay, so if that gets more negative, then because of this negative sign here, that means ln K must be more positive. That means that's got to go up. Oh man. So if you increase the temperature, delta G goes down and ln K goes up. So ln K is related to the equilibrium constant. And so if the equilibrium constant goes up, that means there's more products S reactants in the ratio, and so it means it shifts right. Oh, so A is wrong. A is wrong. It would shift right if you increase the temperature. That's horrible. The next one is the forward reaction is more spontaneous below 300. So that's a bit easier. So if you look at the temperatures below 300, delta G is positive, delta G theta is positive, so it's non-spontaneous. So it doesn't become more spontaneous, it becomes less spontaneous. So B is wrong. C, entropy is higher in the products than the reactants. All right then. So I've got delta G equals delta H minus T delta S. Now, for this reaction, they're saying as you heat it up, it becomes more spontaneous. So as you heat it up, it becomes more spontaneous. So let me put the signs underneath here. So that's going to be, as I heat it up, so that's plus, that's plus, that's plus. And so that's the plus and minus distribution for increasing temperature means increasing spontaneity. The way that I remember this is that this is plus and this is plus, and so that's the one where if they're both plus, increasing temperature means increasing spontaneity. Okay, so the entropy, and so that means the entropy change is positive. Entropy is increasing as the reaction takes place. So that's C. Oh, okay, C it is. That's horrible. Give me an easier one. 17, is it C? Oh, it is C. 17, the highest lattice enthalpy. So let me try to vaguely draw it out to scale. Well, hold on. First of all, I can dismiss this one and this one. So lattice enthalpy, the smaller the ion is and the higher the charge, that's going to give it a higher lattice enthalpy because that's the higher charge density. So the reason I can get rid of those two is that they're plus one and minus one ion, plus one and minus one ion. And I know for sure that calcium's plus two, and that's going to be more attractive. So then the question is, what's more attractive, the chloride ion or the fluoride ion? The more attractive it is, the higher the lattice enthalpy, the more energy you need to put in to break apart the lattice into its gaseous ions. Now, chloride is bigger than fluoride, so that means fluoride must have a higher charge density. It's got a smaller volume, so it's going to be that one. 17D, 17D. 18. So 18. What would produce curve 2? All right then. So excess hydrochloric acid. You've got to keep your eye on the excess here in an open beaker. So open beaker means the carbon dioxide can escape, but everything's going to get lighter. Righty. What change would produce curve 2? Powdering the marble chips and heating. No. That would make it a faster reaction. It would be a steeper curve. 2 is steeper. But I think the trick here is that the starting mass is different. So I'm going to have to be adding more marble chips. Powdering the marble chips and doubling their mass. So B, that could be right. A's wrong. B could be right because I'm adding more marble chips. C, doubling the acid, powdering the marble chips. No. So it has to be B. B's the only one where I've actually added more of the marble chips. And that's what accounts for this difference here. B, yeah. 19, Boltzmann distribution. Oh, this was the most discriminating. So the IB said that people got confused with this and the energy diagram. You know, where there's delta H and activation energy in the catalyst. No. So what represents the activation energy? Isn't it B? It's just B, isn't it? 19B, yeah, 19B. So this line here is EA. Lovely. Some rate equation stuff. The reaction proceeds by the following mechanism. So I got to kind of look to see which one's the slow step, and the IB doesn't tell you. Hopefully that isn't a mistake. What's consistent with this mechanism? All right then. So I'm going to assume the top one's the slow step. And if I can't find the answer, I'll assume the bottom one's a slow step. If the top one's a slow step, it's rate equals K. Take the reactant, that's A. And I see that there's two of them, so that could be that. Is that an answer? Yeah, C, 20C. That wasn't so hard. Is it 20C? Yeah. Just for completeness sake, let's say that this was the slow step. Hopefully that answer won't be present. So if that's the slow step, then I'm going to put B multiplied by the concentration of C. Now you're not actually allowed to do that because B is a reaction intermediate. It was created and destroyed, and I didn't even know it was there. The rate equation can only have the reactants. I didn't know B isn't a reactant. So what makes B? Well, B is made by A squared. Is that an answer? No, so I didn't cock it up. Well done, IB. So the answer turned out to be C. 21, first order reaction. Oh, my brain. So I'm still looking for a quick way to do this. So first order reaction means if you double the concentration, then you double the rate. If you triple the concentration, then you triple the rate. A zero order, doubling the concentration doesn't do anything. Tripling doesn't do anything. So let's see which one looks like that. So this one looks good here. If I double the concentration, I double the rate. So what's that one? Y. So that's going to be Y. Oh. So which other one? And so this is the other one that's good as well. That's also first order. So it's going to be V and Y. V and Y, which is B, 21B. Just for completeness, if it was a straight line, that's going to be the zero order. And if it's some ridiculously kind of steepish, it's going to be second order for that. All right, 21, done. 22. Okay. So let's look at the pressure and the amount of O2, the amount of water. So I want to maximize the amount of methane, or maximize the percentage conversion of methane. Oh, that's a little tricky. So that means I want to favor the products. Well, if I increase the pressure, it will favor the side with the least gas particles. And so I can see on this side that there's 2 gas particles, but on this side there's 4 gas particles. So if I increase the pressure, so I have to decrease the pressure. If I decrease the pressure, it favors the side with the most gas particles. So the pressure has to be halved. So that's going to be C or D. And the amount of water, well, if I add water, that's a stress on the equilibrium, and it's going to shift to the right to oppose the stress. So I need to increase the amount of water. So that will be doubled. So halved and doubled, that's C. So 22 is C. Yep. 23. Is this an ice equation? So it's not an ice equation. All right then. So if I want to increase sulfur trioxide, I've got to have basically more sulfur dioxide and more oxygen, and that will increase the amount of sulfur trioxide produced because of Le Chatelier again. This seems like a similar question to the one above. So ideally, I would increase the concentration of both SO2 and O2, and it looks like that isn't an option. Okay, so then you have to think, well, which one is going to have the most effect? Increasing the concentration of the SO2 or the concentration of the O2? Now, you can see that SO2 is pretty important. In fact, it's there twice. So if you increase the concentration of SO2, it's going to have twice the effect. So it has to be, the SO2 number has to increase the most. So I think that's D. Yes, so is it D? 23D. Yeah, oh, that's horrible. Another horrible one. These don't feel very familiar. Maybe they've hired a whole bunch of new question writers. So there we go, D. So the SO2 has more effect on the shifting the equilibrium because there's two of them. 24, which is amphiprotic. So amphiprotic means it can gain or lose an H+. Well, it ain't that one. That hasn't got an H+ that it could lose. I know that water can gain an H+. It can gain an H+ to make H3O+, and it could lose one to make OH-. Is that the answer? So I think it's going to be C, 24C. Yeah. Just for completeness, I've never seen, if I try to add an H+ to this, it would be difficult to add a positive to a positive, but that would make NH52+. I've never seen that. Nitrogen would have 5 bonds, 5 bonded pairs of 5 electron pairs, and so it doesn't have that. It doesn't make any sense, does it? 25. Solution has a pH of 9. All right then. Okay. So the equations that you might need is pH is negative log H+, or H+ is 10 to the minus pH. And I'll just recap for myself. So if it's 0.001 molar H+, that's going to be pH, what is that? 10 to the minus 3, pH 3. Okay, right. So what have we got here then? So if it's pH of 9, it has to be a base. So it ain't going to be that or that. They're acids. And so this would be POH5, not pH because it's the OH. And this would be POH equals 9. So POH and pH equals 14. So that's going to be pH equals 9, and that's going to be pH equals 5. So it's going to be B, 25B. Yep, 25B. 26, what's a Lewis acid but not a Bronsted-Lowry acid? So a Bronsted-Lowry acid gives away an H+. So if it can give away an H+, this is not what we're wanting. This could give away an H+, so that's wrong. This could give away an H+. It's unlikely to, but it could give away an H+. So I'm left with these two at the top here. So a Lewis acid can receive a pair of electrons, And so let's see which of these two molecules, which of these two species could receive a pair of electrons. Definitely boron can. It's stable with 6 electrons, or it can have 8 electrons. It can have 6 or 8 electrons around that boron. So that's the answer. So 26 is A. Yep. 27, what produces an alkaline buffer? Second most difficult. So an alkaline buffer is made from a weak base and the salt of a weak base. Let's see if any of that's present here. So a weak base and the salt of a weak base. All right then. So I've got weak acid here. I've got weak acid here. Here's my weak bases. All right then. Neither of these are the salt of a weak base. So it looks at first blush that there's no correct answer, but there is. Because, of course, these chemicals react to form a salt of a weak base. So the trick is you need to have excess base, excess weak base. So at the end, when I react, so this is the answer here. When I react this with that, it will make the salt of a weak base, which is ammonium sulfate. And I'll have extra ammonia left over. Oh, so that's my weak base. I put extra in, there's extra left over. So the answer is going to be B for that one. 27B. 28, which is the most reactive. Well, I think the most reactive ends up as an ion. So whichever ends up as an ion is the most reactive one. Now, what seems to end up as an ion here? Well, from what I can see, Z2+, it always stays an ion. It's so reactive, it's already an ion. So the most reactive that ends up as an ion, so it must be Z. So the answer is 28D. Yeah, 28D. 29, what's correct for the redox? Okay, so let's put in some oxidation states. Oxygen's -2 in a compound. That's going to be -1. It's +1, +2. All elements are 0. Hydrogen's +1 in a compound. Oxygen's -2. All right, so reduced and a reducing agent. So the oxidation state, if it goes down, it's reduction. So there we go. That's reduced. That's reduction. And so the oxidizing agent is itself reduced. That's a little psi, remember. So the reducing agent is itself oxidized. So that means this must be the reducing agent because it underwent oxidation. So the reducing agent is the iodide, and what gets reduced is the manganese 4 oxide. So that's A, isn't it? Yeah, 29A. 29A. 30. Oh, electrochemistry. I cut this in college. Maybe I'm in a simulation. I have to do this as a job. First of all, just check they didn't trick us. The most negative one's at the top, just like in the IB data booklet. So I think flip the most negative. Take the most negative standard electropotential one and flip it round. So I'm going to flip this one round. I'm going to put Mn goes to Mn2 plus, and then I'm going to add it to the silver plus here, plus silver. So the most negative one you have to flip around. It needs a bit of cheeky balancing. I need 2 here, and I need 2 here. And to find the voltage, find the difference, make it positive. If the voltaic cell works, it does work. It says it in the question. So what's the difference between those two numbers then? Is that a plus 1.98? So find the voltage, make it positive. So that's going to be D, 30D. Correct. 31, negative discrimination. So the smarter you are, the less well you did on this question. And the more you just didn't really know much chemistry, you did better. That's not a great look for a question. So concentrated copper 2 chloride electrolyzed. So I've got concentrated copper 2 chloride. So I've got copper 2 plus ions, and I've got some chloride ions. Okay, and so it's aqueous, so that must mean I also have H plus ions and OH minus ions. So what's the rule? The rule is the lowest on the standard electropotential scale is preferentially discharged. Oh, for God's sake! So what does that mean? So especially since you don't have it with you. So what's less reactive, copper or H plus? What is lower on the reactivity series, lower on the standard electropotential? And I just know that's copper. So I know copper. Is that enough? No. So copper is going to go to the negative electrode. Copper is going to be preferentially discharged at the negative electrode because copper is 2 plus. So the negative electrode is copper. Is that enough? No, it isn't. All right then. And if it's concentrated, then you get chlorine produced. And if it was dilute, you'd make oxygen. But if it's concentrated, you'll make chlorine. And so it turns out it's concentrated, it's chlorine. So it should be chlorine and copper. That's C. The fact I got it right, that's not a good look because the smart people didn't. Increasing boiling point, so you have to look at the intermolecular forces there. So increasing boiling point, lowest one first. Well, this has London dispersion forces. This actually, if you were to draw it out, has dipole-dipole because this end's a little negative, that end's a little positive, so that's dipole-dipole. And the last one is a propanol, and so that's an alcohol. So that can have hydrogen bonding. Is that a hydrogen bond? It is not a hydrogen bond. That's a covalent bond. Hydrogen bonds are between the molecules, not within. So that's the right order then. So CH3, so that's B. 32 is B. Yep. 33, what's the name of this compound? So first of all, find the longest chain. The longest chain looks like this one here. And you've got to try to get the alkene to have the lowest number. So that means I'm going to have 1, 2, 3, 4, 5, 6. So it's going to be hexene. And I see the double bond is between the 2 and the 3. So it's going to be hex-2-ene. Choose the lowest number. And then I have a methyl group on the fourth one. So it's going to be 4-methyl hex-2-ene. 4-methyl hex-2-ene A. 33A. Nice. So 34. What is formed in a propagation step of a substitution reaction between bromine and ethane? Well, one thing you never ever get is H dot. There's never any H dot. That one's wrong. Br minus must be wrong. Br minus, because this is to do with radicals, these dots, these lone electrons. Br minus, no, that's ions. There's no ions in this process at all. And so that just leaves me with A or B. Well, I happen to know that B is formed from 2 of those. That makes a B. And so that's actually a termination step. 2 radicals make no radicals here. So the answer must be A. The answer must be A. Is it? Yeah, 34A. 35, what's most likely to hydrolyze via SN1 mechanism? Okay, so I think 1, 2, 3, bang. 1, 2, 3, bang. So SN1 is 2 steps with a tertiary haloalkane, and bang means it's fast. So the question's really asking, which is a tertiary haloalkane? And I think it's C, isn't it? So find the halogen, find the carbon attached to it. How many carbons directly attached to that one? 1, 2, 3. So that's a tertiary haloalkane. So 35 is C. Yep. 35 is C. 36. You just have to know this one. That's A, isn't it? 36 is A. You just have to know it. I got it wrong. Yeah, I didn't see the little cheeky benzene ring there. So yes, it's C, isn't it? It's C. I didn't notice the benzene ring there. 37, how many chiral centers? So a chiral carbon is a carbon with 4 different groups attached. Let's have a look here then. So this carbon has 4 different groups attached. So that's 1. This carbon here has 4 different groups attached. This one has 4 different groups attached. This one here, did I miss out? I missed out an OH here. So that has an OH. Yeah, and that's 4 different groups attached. So 4. This carbon doesn't count because it has 2 hydrogens. Nor does that one. Anything else going on? No, so I think it's 4. 37C. Yeah, 37C. Nearly done. 38. Why didn't it work? So if your value is lower, that is from heat loss to the environment, you thought you transferred all the chemical energy to the water into thermal energy, but you lost some along the way. So it's heat loss to the environment. What could have contributed? Not all the heat of combustion was transferred to the calorimeter, so that's correct. Incomplete combustion. Yep, maybe you just didn't burn as much as you thought you did. That's why it didn't get as hot as you hoped it would. The temperature probe touched the bottom of the calorimeter. I don't know about that one. What about 1 and 2? Is that enough? No. Okay, if it touched the bottom of the calorimeter, I suppose you're not really taking the temperature of the water, you're taking the temperature of the metal. It's touching the bottom, and really it should be in the middle of the water. So would the metal be hotter? I'm trying to think, would I rather put my finger into the water or touch the metal? I think the metal would be hotter, wouldn't it? the metal will be hotter than I expected. Let me look at the question again. The final result was lower. So if I touched on the metal, I'd have a higher temperature. So I think it's just 1 and 2. I'm not sure. A. 38. A. Yes. 39, most difficult. This is because there's two contrary IB rules working on this, I think. So what's the mean titer at the end? So one of the tricks they have is that you should ignore the rough titration, the one you just rushed at the beginning to get a general value, but it doesn't seem to be any there. So let me take the average. I don't think I need to. It's 11 point something, isn't it? Let me have a think. All right then. So if I've got 11.35 and I'm down to 0.20, if that's plus or minus 0.05 and that's plus or minus 0.05, then the difference, just for this first trial, is going to be 11.15 plus or minus 0.1. And so there's the potential for confusion. I added up the uncertainties to get this uncertainty here, but you can't really. There's a disconnect here. I'm claiming I know it to two decimal places here, and yet I'm uncertain to 1 decimal place. So what am I going to go with? Well, I think I'm going to claim that I only really know it to 1 decimal place. So I'm only going to be needing 1 decimal place here for this first trial. So I want 1 decimal place and an uncertainty of 0.1. That's A. Is it 39D? Oh, that's not fair. Oh, so I actually had to work out the average. So it's 11 point. Oh, I see why people got that one wrong. Is it 11.1 or 11.2? How silly is that? Okay, so that's D. You actually have to work out the average. That's not fair. Not so late in the paper. And 40, H1 NMR. So I've got 2 peaks, which means I've got 2 sorts of hydrogen environments. Well, let's have a look. Propane. So propane has 2 hydrogen environments, and the ratio is going to be 6 of these. 1, 2, 3, 4, 5, 6 to 2 of those. So it's a 6 to 2 ratio. Maybe. Propanone. So for propanone, I've only got 1 hydrogen environment. All of those hydrogens are identical, so that should be 1 peak. So it's not that one. Next one is propanal. Propanal. I've got these 3 hydrogens are the same. These 2 are the same for the second environment. And there's a third environment here. And so that's going to be wrong. That means 3 peaks. And so 2,2-dimethyl propane, I know that that's only got 1 hydrogen environment. So the answer is A, 40A. And we're done. That was pretty nasty. I do detect a different author behind these.